This is Greg Caltabiano from Atombeam, and I'm very pleased to invite you to a discussion that we're going to have today on Atombeam products, technology, and especially its relevance and importance in the data processing, data communication world of today. I'm especially pleased to be able to interview and ask questions to Josh Cooper, who is the chief scientist at Atombeam and responsible for a lot of the theoretical underpinning and development of this product. So again, thank you for attending. I thought it best if I start off by talking about a little bit of the background as to why this is so important at this stage of the evolution of our technological world. So what really is the basis for this is that everybody knows that we've had this incredible increase in the amount of data that is being created and consumed. But I think until you look at the numbers, until you see statistics, it's hard to get a handle on just how big that explosion has been. The statistic that always just amazes me is that 90% of all the data in the world has been created in the last 2 years. That's just amazing. It tells you about the acceleration of data that's going on right now. And as you would expect, as we look forward, every 2 years, we're expected to create another doubling of the amount of data that we currently have right now. So this is a tremendous, tremendous exponential increase in the amount of data. So you're probably saying, well, why is this happening? Why is this happening now? And I think we need to look at the sources of that data as well as how that data is used. So on the sources of data, one of the things that we all live every day is the smartphone revolution. And in the US, we see most people with a smartphone, but actually, if you look at the statistics, it's 100%. Some people have 2 smartphones. Maybe there are people that don't have smartphones, but they're overwhelmed by the people that have 2 or 3 smartphones. But even when we look around the world, there's roughly 8 billion people in the world, and there's over 6 billion smartphones that are in operation. So that's about 80%. So yeah, that's a tremendous amount of phones. And these phones are used differently than phones used to be used in the past. In the past, phones were used to make phone calls, to send text, but now phones are used especially with applications. And these applications create data. They send the data back to the cloud in each direction. And so this is creating data, transmitting data, processing data, storing data. The second thing is IoT, the Internet of Things. This is also something that has exploded in size. IoT means sensors in the home like smart thermostats, smart doorbells. It means factories where data is created from sensors on machines and in different parts of processing. It's data coming from cars, trucks, trains, airplanes. And this is, again, an explosion of data creation. And of course, our computers haven't stopped creating data. But the data would not be created at this rate if there wasn't a good use for it. And this is where artificial intelligence, machine learning comes in. What we've developed over the past 5 years, and again, this is accelerated over the last several years, is the ability to take this data, look at patterns, make decisions, provide, and of course, for these companies, that means making a lot of money. This is Google and Facebook, but also many, many, many companies out there. And one of the characteristics of artificial intelligence is the more data you use, the better your AI, the better your decisions, the better your predictions. So there is a desire to suck up and create as much data as possible so that that can be used. Now, how are we handling that? How is our infrastructure, our data processing, data communications infrastructure handling this? Well, fortunately, we've had a lot of technical innovation, starting with Moore's Law, which says that as we create semiconductors, every 2 years, we're able to double the density, which means that every time you buy a smartphone or a computer every few years, your processor is running much, much faster. The same thing has happened with memory, where, again, every time you buy a computer or a smartphone, servers and data centers, the amount of data that can be stored per dollar has gone up dramatically. And of course, the same type of thing is happening with communication. The amount of data we're able to send over optical fibers, over wireless. So these innovations are really important. But as good as they cannot keep up with this data explosion. They're just not going fast enough. The data is being created and consumed much faster. So there needs to be other ways to solve this problem, in addition to the technological innovation. One thing that's happened is that companies are trying to process more data closer to where it's consumed. So your cell phone may try to process data of some types of data for some types of applications without sending all of it back to the cloud. And we're seeing more and more of this. The other thing that's happening is that companies are saying, well, I can't send all the data back. I have to just erase some of it or select some of it. And they say, what choice do I have? We're just creating too much data. But of course, when you do that, you're reducing the potential for extra AI accuracy and training. What if you didn't need to do that? What if there are ways where you could send back more information, but actually transmit fewer bits? I know it sounds like magic. It sounds like something that's a contradiction. But this is what Atombeam's technology is all about. And we're going to talk about it, talk about how it works. And I'm going to ask Josh first. It sounds like magic to me. Can you tell me, how does this work, and why is it possible to do it now and not 10 years ago?
No, thanks, Greg. So, in fact, the basic idea that underlies the whole technology is an entirely straightforward one, namely abbreviation. The idea is that if you have messages that are coming across all the time, as all of our devices are transmitting data here and there, if the message is the same as previously sent messages or closely resembles them, you could just send a message to that effect. Instead of resending all of the data, just send an abbreviation. It says, you know what, the temperature today, same as yesterday. And over time, this can mean sending fewer bits. That basic idea, turns out, is incredibly powerful. And this is exactly some of the core idea that came up starting in around the 1940s with the work of Claude Shannon and others, that ultimately turned into what we usually refer to as compression these days, where one takes data and searches through it for patterns, and then uses those patterns to abbreviate common and repetitious messages, so that the amount of data that's sent is less than what was generated in the first place. Now, that idea, of course, is an old one and works well, but has some serious limitations. One of them is that it doesn't work if your data is just very short messages. If you've got very long files, then one can build heuristics to trawl through them looking for repetitious patterns and then try to take advantage of those patterns by rewriting them with shorter notes. Oh, this is the same as something we saw previously. But one then needs to encode in the data that's sent the instructions for unpacking it back into the original data, or else it won't be possible to restore it to the original data. Of course, that means that it's not useful. This works well if you've got a very large file, and it works well if you have well-designed heuristics for finding patterns in your data to rewrite and to abbreviate. The problem, as I mentioned, is what happens when you run into very short messages. When you've got, let's say, to use your example of the factory floor with, let's say, temperature sensors located all over the place. They're just sending out very short messages, brief bursts of a few bytes at a time, say, that encode a temperature or something of this form. Well, then, if you're going to bake into the messages that have been compressed, the instructions for decompressing them, they're going to get bigger. They're not going to get smaller, this is a serious problem. So basically, compression is useless on very short messages. and very short bursts of data, it's not possible. Fortunately, we live in an era when a new paradigm has emerged, that of AI, or more specifically, machine learning. The basic idea is, instead of trying to handcraft clever heuristics to find the patterns and to find the way to abbreviate them most efficiently, let's let the machine learn. So the basic idea that underlies essentially all of modern AI, which has of course been enormously successful, is to take data that's representative of the kind of data one expects to actually operate on, and let the machine learn from the data what patterns are present, because those patterns can be taken advantage of in a variety of ways. In this context, it would be to find efficient ways to abbreviate them. That paradigm is very new. That's something that in the past, it was a very natural idea for a very long time for engineers, computer scientists, statisticians, mathematicians to think, okay, let's try to craft clever heuristics to solve this problem. But that's been replaced in many different areas with learn from the data. And because we've got such a glut of data, this is actually very possible. Because we have the computing equipment to do that learning, this is possible. This has enabled the machine learning or AI revolution, that we're able to get tons and tons of data and learn from it in a way that makes all the different processes that are operating more efficient. So it's really a matter of having this new paradigm of learn from the data, the central paradigm of artificial intelligence today, and then also the enabling equipment to do it, the computing hardware, even the theoretical infrastructure to describe the systems that are operating. Are getting very, very complicated, very complex systems. But there's a flip side to having all of these amazing devices. We have supercomputers in our pockets, which is that they are generating such a, as you alluded to, a tremendous amount of data. And so this is something that needs to be managed. And so we have a new need as well. In addition to having this sort of change in philosophical paradigm about computing, we also have a whole set of needs that have arisen because of all the amazing developments in technology, as regards computing, communications, storage. All of these technological settings have introduced new and difficult problems with the enormous amount of data that needs to be sent over lines that are restricted in bandwidth, and sent by devices that have limited power, and stored in places where there's just limited room. We're running up into these limitations all over the place. And so that's created a need that's made us dig deeper into the theoretical tools and try to apply this learn from the data, the machine learning paradigm, to essentially all computing problems. So that's really what Atombeam has tried to solve, and been able to take advantage of this new way of thinking about how to do computing.
That's exciting. So Josh, tell me, where do you think this will first be used? And then after you talk about that, tell me where you think, how pervasive will this be?
Yeah, so one of our first and key applications is IoT, Internet of Things devices, where like the temperature sensors on the factory floor, you've got these small devices that have limited power, limited computing capabilities, constantly transmitting data, and that are costly, especially if they're using limited bandwidth channels like satellite. Satellite is a place where Atombeam can provide a tremendous amount of value to whoever's operating or using the communication lines, because it's very expensive to send messages up to space and back, and it's also we have very limited bandwidth for doing so. So any situation where there's these aggressive limitations on what the user has access to or how much it costs them to use it, Atombeam has been very successful in addressing those kinds of problems. And I do think there's a lot more applications out there where Atombeam's technologies can be applied and can save money, can save time, can save power, and can mean sending more data for less. This is IoT devices, like you said, are proliferating. They're in every dishwasher, every factory in the world, so they're just absolutely everywhere. And the communications between those devices and gateways, or between computers in a data center, or even between chips or cores on a single chip. These are communication environments that have some severe limitations, and they're absolutely everywhere. So Atombeam can play a role in all of those settings that are becoming increasingly pervasive in our lives, to improve the performance and to reduce costs.
Yeah. So is it correct to think that when we look at communication, there's limited channels, limited capacity in each channel, but also to send more data, you have to usually transmit more power, which means your batteries go down faster, or you use more power from the utilities. It costs more to send more data because you need to have more sophisticated electronics on both ends, or you need to use more bandwidth, which can be expensive. So it sounds like anytime you're transmitting information, there is some incremental cost to that. And therefore, if you could reduce the amount of data that you need to send the same information, it would always be an advantage. Is that a correct view, perspective on this problem?
Yeah, absolutely. And there's all kinds of trade-offs. Some of them are quite subtle. You mentioned the sort of most obvious trade-off, which is that, well, you need power to turn on your antenna, or send a message across a fiber, or transmit up to the satellite. I mean, this requires more data, means more power, which means drawing down on your battery, or paying for electrical costs, et cetera. But there's even subtler issues. For example, there's always a trade-off in communications with satellites where one has to think, do I increase the amount of power that I'm using to send the transmission, or do I allow there to be the occasional error? Because this is something that all communications indeed have to deal with, even in very controlled environments, but especially space communications have to deal with bit flips that come from background radiation or cosmic rays, all kinds of different sources, capacitive crosstalk, things like that. And well, you can introduce ways of fixing this. This also actually goes back to the very early days of information theory, using error correcting to fix these problems. But that's costly as well, because there's additional computing involved. There's additional power needed to run the machines that are doing that computing. And it means eating up more bandwidth, because the error correcting bits that get attached to a message are using some bits. So if you can make more space for error correction, you can have higher fidelity in your messages, or get away with the same fidelity for a smaller power budget. That's right.
Yeah, interesting. I talked before about the way that data processing networks and communications networks are trying to do more processing on the edge. And one of the benefits, of course, is that they can send less data back, but that it doesn't seem to be doing enough. And if they combine that with using Atombeam technology, they would be able to send more data back to central places and be able to then have more effective, efficient machine learning in their algorithms, because they'd be having more data. But one of the concerns they may have is, if we introduce extra processing to do the encoding that we talk about, that there could be a big increase in latency. Can you talk about Atombeam's architecture and how it does not increase latency, and why?
Yeah, absolutely. So, in fact, Atombeam's technologies have been designed from the ground up to try to minimize latency. And indeed, the basic idea of separating the process of finding patterns from the data that's actually sent is at its core about offloading the heavy lifting of the computations you're referring to a pre-processing stage. So indeed, when one runs Atombeam software, the first stage is to build a code book that has been optimized for a particular kind of data. That's really the hard part. And it can be done on a machine that doesn't need to run live when the data is generated or needs to be consumed. So this is done as a pre-processing stage. And then at runtime, the computing need is actually very slim. And it's been designed especially for that purpose. So even the instruction set it needs is very limited. Mostly what happens at runtime are lookups. It's just memory lookups, which means that very limited processors and very limited power budgets can handle it. Also because of that, we're able to get the latency of the software really low. So instead of having to sit around and wait for enough data to accumulate to even bother compressing it, we're able to compact, that's the term we usually use to contrast with compression. We're able to compact the data after just a few bytes and transmit immediately. So if the data perhaps would, you have to wait around for an hour for enough to accumulate for compression to be worthwhile, we're able to send right away. And indeed, we're constantly on an ongoing basis getting that latency closer to zero, trying to reduce the amount of time between when the data arrives and when it's encoded. It's, like I said, it's a very simple computational step at that stage of the game. It's enabled by this heavy processing that's happened in advance of that stage, of the runtime stage. But at runtime, it's actually very, very light lift computationally. And so we're able to do it very fast and with a low power budget, and even on a very limited instruction set, very limited chips in terms of their complexity.
Yeah, that's very interesting. Very different than standard compression.
Yes.
One of the other things that I've heard, especially criticisms of IoT, as we put thermostats and devices are in dishwashers and laundry machines and refrigerators transmitting data back. The kind of alarming statistic is the vast majority of all that data is sent absolutely in the clear, meaning that anyone snooping can read that data very, very easily. And I know that this is not, that Atombeam is not a security company, but how can Atombeam, when it's used, help make this problem less bad?
Yeah, you hit the nail on the head there. There's a huge hazard, security hazard and privacy hazard coming from this proliferation of IoT devices in our lives because they're sending data almost entirely in plain text. It's not transformed in any way. Anybody with an appropriate receiver, which is sometimes very inexpensive, can eavesdrop and even inject data and disrupt operations. These are major hazards, and you'd think we would have learned from the early days of the internet when things weren't encrypted as a matter of course, and now everything has to be retrofitted with encryption, very expensive, and it's difficult in terms of the infrastructure. Well, Atombeam, because we're ingesting data and then encoding it before it's transmitted, it's encoded in a way that's opaque to an eavesdropper. So it's not where it can also be wrapped in standard encryption algorithms. But actually, even without that, there's a kind of deep obfuscation happening that will frustrate all but the most determined or resourced attackers. So by using Atombeam, not only do you get all the benefits of better bandwidth savings and power reduction, et cetera, but in addition, it's obscuring the data so that it improves its security and privacy profile, and reduces these kinds of hazards.
I wanted to ask about something a little bit different. As data is passed from the source of the data to various stages of processing, it's often necessary to actually do some processing on this data. If the data is encoded close to the source, is it possible that data could actually be processed, that we could do some searches or actions on that data without having to de-encode it?
Yes, and this is a really neat feature of the encoding. That it's funny, we didn't even really realize it until after the core functionality was built, that Atombeam encoding has this amazing property that one can essentially just start reading from any point within the data. There's a true random access property to it, which means being able to read the data without decompacting it, without restoring it to the original. It's even, you can store less data, this transmitted encoded data, and not worry about unpacking it until later, because it's searchable as is. So you can read it, you can search it in its compacted form, and even run analytics on it. So that the data is entirely readable, which means that essentially any transformation, any analytics that could be performed on the original data could be performed on the compacted data as well. We've got fully functional prototypes of this, the random access capabilities, the search capabilities, and the reading capabilities. Those features are being increasingly integrated into the system in the near future.
That's very exciting. Well, we don't have a lot more time, but I wanted to ask one last question. About your background. What in your background, can you explain what in your background allowed you to see these opportunities, to be able to look at this problem from such a different perspective?
Yeah, so I'm fundamentally a mathematician, and sometimes that evokes an image of sort of very, very abstract and ideas and methods that are sort of disconnected from reality. But and of course, I do deal in theory all day, but without a tie back to material reality, this stuff can get unmoored. And so yeah, I've always had an interest in applications and how they inform theory, and also how, of course, the road goes both ways. The theory informs practice, and practice informs theory. And indeed, my background is in combinatorics, or discrete mathematics, which is a kind of close relative of theoretical computer science and overlaps with it in lots of ways. And the whole history of this subject, this discipline, is one of a back and forth with computing. This is an area, discrete mathematics, that matured in the context of our modern computing era, and so has been in conversation with computer science from day one. So I've sort of always lived that life of both the mathematician and the computer scientist. And I think they have a lot to say to each other. My work has always involved both. I have, in addition to my experience in research and in academic settings, something like 20 years of industry experience, because I don't know, the theoretical questions get dry without some hands-on problems to solve. And there's always, industry is always coming up with interesting problems that you couldn't possibly anticipate without seeing the needs arise. And they've been, like I said, very influential in mathematics, in particular the areas that where my background is strongest.
Josh, thank you so much for your very clear answers to complicated questions. And we're very fortunate to have you working on these problems. It sounds like there's huge progress being made, and this will make a big difference in how we're able to handle all this new data that's coming into the system every single year. So thank you again, and thank you for listening.
Thanks very much.